I'm passionate about the mechanics and physics of ice sheets. And it's really from the micro scale, so from millimeters, to the continental scale, where you have thousands of kilometers. There is so much physics and mechanics going on. It's an uttermost challenge to understand how they work, how they function, how they change over time, and also how they will evolve in future. So the ice sheets have changed quite dramatically in the past 30 years. And they both together, Antarctica and Greenland, contribute about a third to sea level rise. So we have some pressure to understand the physics behind it very good. But they are complex beasts. I mean, they're fascinating, really, truly fascinating, but they are really complex. But what does that mean? So one part of it is that many of the processes are nonlinear. And nonlinear means that if you double the input, the output is not double, but maybe triple or just half. But that's not all. The problem is that there are very many processes and that they interact with each other. And this makes them so hard to understand and to model, to simulate also. Now, how does it work in general? Well, if you look at ice sheets, they are mainly formed, of course, from snow deposition. But then you only have snow, so you need to compact the snow to produce some ice. And that's what's happening in nature. And it's not so much different from when you have a ceramic mug at home. When this is formed, you also start with a powder. Imagine the snow to be a powder. And then you are compacting it, and the grains are settling, they get in contact with each other, and with more pressure you have, and that is more and more snow load from top, as more compressing you are, and at the end you are forming ice. And it's not just a meter of ice or so, of course, it's about 3,000 to 4,000 meters of ice. And if you take a look at this here, you can see how the ice at the base of an ice sheet looks like. This is me playing with an iceberg just in Iceland at the beach, more or less. And you can see that I try to pull out one of these grains. Yeah? So at the base of the ice sheets, they are quite large. At the top, they are rather a millimeter or so. And what is the most interesting thing of this is you see how hard the material is, how difficult it is to get it out. But what's the super cool thing with it is it basically behaves like a fluid. Well, of course, in a frozen state, it's water in a frozen state, but the motion of glaciers is following also the same behavior as fluids are. So if you have at home a pot of honey and you turn it upside down, you may see it creeping, flowing. And this is also what you see here at the Elephant Foot Glacier. This Elephant Foot Glacier is showing quite nicely how actually the structure of such a motion is. Yeah? It's similar to what you would expect with your honey to happen. But it's not only that the ice is kind of moving due to this viscous fluid behavior. You can also imagine that if the base of that glacier would be lubricant, like imagine you would put honey on an oiled plate or so, it could move faster. And that's also what's happening in ice sheets. So here I show you a cross-section, just a sketch through an ice sheet. And the velocity, the speed with which the glaciers are moving is in the order of a centimeter to 10 centimeters per hour. Of course, compared to a car, super slow. They are more crawling than they are running. But if you imagine this really large mass of ice is moving with such a relatively high speed. And if you have now at the base of the glacier just a little bit of water, then it also slides over the base. And this is what makes many of these areas moving fast, what may also be one of the key reasons why ice streams form, although we have not yet entangled the processes entirely. But now imagine you would want to learn more about how this ice is moving across the base, but you can't reach it because you have 3,000 meters of ice on top of it. You want to go there and put some instruments down there, but you just can't. There's no chance to do that. And that's a bit symptomatic for glaciologists, actually. We can measure with satellites from space how the velocity of a glacier is at the surface. We can measure the retreat. We can also measure if it thins, but we cannot access anything from the base. And it's a bit like you would have a forensic doctor and you ask him to say what is the reason why a person died, and he's not allowed to slit the corpus. He cannot take any samples, right? But of course, it's not just as simple that many bullets have hit that person. But there's one more thing allowed in the game, and that would be X-rays. And what is for him an X-ray is for us radar, because radar ice is transparent for radar waves. And that's really cool, because it allows us to survey the thickness of the glacier. And that's what we actually do on board of our aircrafts. So here you see an image, and it's one of our aircrafts equipped with a radar. So we are sending out radar waves, and they are getting a return from the base of the glacier, and then we are recording the returned signal. Well, and if the base of the glacier is wet, then the strength of this radar signal is higher. And this is one way to infer if the base of a glacier is wet. But even now, in the year 2022, this data is really sparse. Yeah, you could also go and discover a mountain underneath the Greenland ice sheet still, or a canyon. You just need to charter an aircraft, put one of these radars, they are of course expensive on it, and get a stress-resistant pilot, because this is quite tricky to fly over these ice sheets in the way glaciologists would want the pilots to fly. And believe me, our pilots, they are our heroes, the whole crews, they make our science possible. And actually, with these types of surveys, we can investigate how the base of the glacier behaves, a bit of it, right? And what we've learned over the past years is that there are vast areas of the ice sheets that really have water at the base. But where does this water come from? So one thing is, the ice sheet is resting on the Earth's crust, on the lithosphere, and there is some heat coming from this lithosphere going into the ice. And at many places it is enough to melt the ice, and even just a little bit, a millimeter per year, is enough to have some lubrication. But why these laws that may be able to describe how this ice is sliding are not well known. And one thing we know is that the roughness of the base is one of the factors. They could be rough as a sandpad or rough as a corrugated iron. Yeah? You don't really know exactly the scale of this roughness, but with this radar data from these aircrafts, you can at least infer some topography and get an idea of if it's rough. One thing we definitely know is if the water pressure underneath the ice is high, then the ice is moving faster. But as if this would not be complicated enough, we know that the glaciers in Greenland move faster in summer than they do in winter. And you probably know yourself already why is that so. This is because there is melt at the surface of Greenland going on in summer. But now this melt needs to deliver the water to the base, right? It's not enough to have water at the surface. And this is what we just learned in the past years, that every year we find that in summer the velocity is higher and that this is really correlated with the melt. So some way or the other, the water makes it down to the base. And one way is working like this. Here you see an image that we took in the field, and don't worry about this disco ball. This is just there to make it easier for the helicopter pilot to see my instrument and to land there. But you see how much soaked the surface is, right? You would need valleys to go there in order not to get wet feet. And just a few days later, you would see something like this. This is a picture I took with the onboard camera of our aircraft last July, and you see all these rivers. These rivers are filled every year, and they don't exist more or less for a long period of time. It's just a few weeks, but they deliver this large amount of water into the so-called Supraglacial Lakes, and that's what you see here. And In our study area, the largest lake has a size of about a fifth of the area of Paris, which is quite large. It's just one of these lakes. Yeah? There are many of these lakes. And the most crazy thing is that the water is going down from one of these lakes in just a few hours. It's really absolutely fast how you deliver the water to the base. And the amount of water is incredible too. If you would fill the entire area of Paris by 1 meter with water, this water goes down in just a few hours to the base of the glacier. And we can measure the response of the glacier. Here is another picture from our onboard camera. And maybe you take a second to look for an unusual pattern there. And I know it's hard to see, but you may recognize that there is a small spot. And this is how one of my GPS stations look like if you fly over it in 700 feet elevation. So this is how it looks on the ground. In the left side of the image, you can see the antenna that is receiving the GPS signal. And on the right side, you see my battery box and some solar panels. And this station is located close to one of these large lakes. And after the lake drained, it just takes a very short period of time, just hours, then the glacier starts to accelerate. It doesn't last for long. It lasts only for a few days. And then the water has made its way probably somewhere to the ocean. Now, this source of fresh water has not been taken into account by glaciologists or oceanographers very much in the past, but we learned now that this is a really important process that we have to take care of. But as if this would not be complicated enough, if we just go back, and you may see here these stripes, yeah, these lines. And each of this stripe is a crack. They may be long as kilometers and wide as, like, say, 10 meters or so. But every of these cracks is a representation not of a fluid. You recall, a fluid would not be able to have a crack. And I recall very well when my son was a bit younger, he came into my office at home and I was staring at a satellite printout of a glacier. And he said, "What are you going to do?" And I said, "Look, there are these cracks, but it's a fluid." And he said, "Mom, there can't be any cracks in a fluid." And I think he just thought, now she's getting crazy. But today he is computing by far more crazy things than I do, I must say. Yeah. But indeed, it is a super strange thing. It does not only behave like a fluid, it also behaves like a solid. And that's why we have these cracks. And these cracks are the locations where the water makes its way to the base. And here you see also just a simple movie that I took with my cell phone during a flight campaign last July. You see the surface of the Zacharias Isbrae, you see a lot of cracks there. And of course the cracks are the reasons why at the end you are detaching icebergs, what we call calving. And calving itself is a natural process. It has happened ever, and it will also happen ever in future. There's no doubt about that. But in some areas, we discover that the floating tongues, as we call them, of this ice sheet, they are disintegrating. And this is not a normal process. And the glacier you are seeing here, that has had this experience. It has lost its floating tongue, and it starts to accelerate. And that goes even 200 kilometers upstream into the inland. Yeah? And these are really the signs of change on the Greenland ice sheet. While if you look back, and you may just want to think a second about what kind of complexity may you be able to describe or not, then if you look at this quote from Einstein, so make everything as simple as possible, but no simpler. This is our daily challenge, really, to select what kind of complexity can we really incorporate in our simulations, in our studies, and what can we not simulate well. And in the past years, we made quite a lot of progress, but there are still so many things to tackle. And often I think, like, engineers have solved sintering. They can compute cracks and so on. But we can't do any experiments in the lab. And we don't have any simplified setting. It's just nature doing an experience for us. And this experiment is what we need to observe to learn about the dynamics of the processes of the ice sheets, right? So they are fascinating, complex beasts, and I thank you very much for your attention.